What's up, calculus students? Sliding into the second half of Unit 5 on calculus word problems, where we are going to uh, take a derivative with respect to something other than x. We're not really worried about dy dx anymore. Dy dx, we should be comfortable with understanding means like instant change in y over instant change in x, which means slope or tangent slope. Now we're going to concern ourselves with how things are changing at a moment in time. So we're going to get this dt, which is like how things are changing at a moment in time. Like you hit your stopwatch, how are things changing right there? So things are going to be moving, and we're going to just like pause the movement and say, how is, an X position changing at a moment in time? How is a Y position changing at a moment in time? How is a radius of some circular object changing at a moment in time if that circular object was expanding or contracting? How are distances between two things changing at a moment in time? How are angles changing between two things at a moment in time? And this really is our first like real world application of calculus, seeing how objects are changing in a real world situation. To the heart of the matter, we need to be prepared to not take derivatives with respect to x, but rather with respect to t. Now, we talked about in class how it doesn't matter what you have as long as it's not t's, you will have a d blank dt after your derivative. So if you're taking the derivative of a, you're thinking of it as like the derivative of x, which is 1. So you're going to say like, okay, the derivative of a is 1, but then times dA dt, just like having the dy dx after derivatives of y's. The derivative of b squared, well, the derivative of b squared is like the derivative of x squared. It'll be like 2x, so it's going to be 2b, but we will have a dB dt after this. The derivative of 4 is still 0. There's nothing crazy about that. There's no d something dt after that. And we now have a change equation. This is like how A is changing. This is how B is changing. We can see the relationship between how A is changing and how B is changing relative to B's size. We're given information here. We're trying to find dB dt, which is that. We're told when B is 3, I can just plug in the information I have and then solve for whatever I'm trying to solve for. We got dA dt is 2. Sorry, dA dt is -4. I don't know where 2 came from. And we'll just, algebraically solve. Add the 4, divide by the 6. And it's like 2/3. 2/3 what? Units per second, units per millisecond. It doesn't matter. Like right now, we're just getting used to things. Okay, here's an equation with x's and y's. It's the equation of a circle radius 5. We're thinking about maybe something moving along the circle. And we're like, if we have this point on the circle, and this is changing like that, how is the x distance changing? And you don't really have to understand what it means. You just got to be able to do it. We'll talk about, we talked about a little bit what it means in class, and next class we'll see more. We see this as like a variation of the Pythagorean theorem. Equations of circles just come from the Pythagorean theorem. And we'll see whenever we're taking the derivative of the Pythagorean theorem, we could drop the 2's if we wanted to. Divide everything by 2, and we get this. So just preparing you for that. We are trying to find dx dt. We have y is 4. Sorry, x is 4. We got y is 3. dy dt is -2. I didn't even like bring up the fact that I'm wearing a hat right now. Yeah, it's cold outside. This is my first cold video. So eventually it'll get too cold and I'll have to find a room but like there's no rooms open. So get Mr. Mester with the hat on. All right, we're going to see this a lot next class. Just we use the Pythagorean theorem to help find diagonal distances, turn it into a horizontal component and a vertical component. How is d changing at the moment where x is 2, dx dt is 5, y is 3, and dy dt is -4? I'm kind of giving you a hint of what to do, and I'm going to show you why. We're using the Pythagorean theorem. If we take the derivative of the Pythagorean theorem, we get this. And we can divide everything by 2. Okay, and this is like our change equation for motion or for distances. Cool. If we start plugging in stuff, we got 2, 5, 3, -4. I'm trying to find dt dt, but I don't have d. This will happen a lot. The key is you'll get your change equation. Sometimes you'll have to find a piece of information that is missing using the original equation. So at the moment in time, when x is 2 and y is 3, we could find d. And a lot of questions will arise of like, why didn't we just plug in 2 and 3 at the beginning and just get the 13 equals d squared and just use the derivative of that? Well, it's like x is not always 2, y is not always 3. We're talking about a triangle that's changing, and we are like hitting a snapshot. So we need a change equation with fully x's and y's being variables, not being numbers. We can't say plug in 2, plug in 3 into the original equation. We're going to take the derivative of our original equation as it is to get our change equation. And we might need to use our original equation to find missing pieces of information. -12 plus 10. Cool. All right. So that's just like warm-ups where like you didn't have to really come up with the equations yourself or write down any information. Everything was kind of given to you. But now we're going to talk about real world situations. And we'll talk about lengths changing. We'll talk about areas changing. We'll talk about volumes changing. And what's important is that if you're talking about units cubed, cubic units, I should have done units in the first power here, but if you're talking about cubic units or units cubed, you're talking about volumes. Lengths times widths times heights. You know, there's 3 dimensions of units being multiplied, units times units times units, units cubed. If you get squared units, remember you're talking about areas. If you got units to the first power, you're talking about lengths. So volumes, areas, lengths could be radiuses, lengths could be x distances, it could be y distances, it could be a height, it could be a width, you know, stuff like that. Okay. So like you're going to have these word problems, and a word problem could involve this information: air is being blown into a balloon at a rate of 10 cubic feet per second. That is how volume is changing. So we will write down a calculus notation change statement that like dv dt, the change in our volume at moments in time, is equal to 10. The surface area of a square is increasing by 4 meters squared per second. That's an area. That's a change in an area. That's a dA dt. You can say 4. Units are not important, but units for our answers, but units are important to understanding what's happening, making sure you're doing the correct thing. A circular cross-section of a sphere is growing at squared feet per minute. Oh, that's an area. Height of the water is decreasing by 4 centimeters per second. Here comes another thing that's important. What do we know about things? If a derivative is positive, you would know h is increasing by 4 centimeters per second. If your derivative is negative, you would know h is decreasing by 4 centimeters per second. Keep in mind that if your derivative is 0, h is constant. It is flattened out. It is fixed. And I'm just talking about understanding derivatives and their signs and what they mean. If a slope is positive, if a derivative is positive, something is increasing. If a derivative is negative, something is decreasing. All right. This is kind of like the next level up where I'm not giving you information in terms of like dx dt equals this, dy dt equals that. You're going to have to change the statement into calculus notation. So you have this equation, w equals x squared y. This is like our central equation, which we'll need to find a change equation for by taking a derivative, which I'll do in a second. But here, x is decreasing at a rate of 2 units per minute. X is decreasing. That means its derivative must be negative 2 units per minute. Units, not units squared, units to the first power length. Y is increasing at a rate of 3 units per minute. How is W changing at the moment when X is 4 and Y is 5? Okay, so this is like the next level up where we have to get that information from our problem. We'll use the product rule. Product rules exist, just when you're taking derivatives of x's, it has a dx dt afterwards. Y's, it has a dy dt afterwards. We're finding dw dt. We have all the information we need. X is 4. Dx dt is negative 2. Y is 5. Dy dt is 3. X is 4. Let's figure this out. So negative 10 times 8 is negative 80. 3 times 16 is 48. 12, which means W is decreasing by 12 units per minute. The surface area of an object can be determined by the area of its base, such that the surface area equals e to the b, where SA is surface area and b is the area of the base. Determine how quickly the base area is changing, given the surface area is changing by 10 squared feet per second when b is 5 square feet. Okay. How quickly is the base area changing? Okay, that means I want to find dB dt. When the surface area is changing by 10 squared feet, so that's like a dA dt, at the moment when b is 5. So we have our equation, which we'll need to find a change equation for. How are things changing? Well, the change in our surface area at a moment in time will be given by, okay, now how do we do e to the b? You can O and I this. You got e to the parentheses and you got b. B's derivative with respect to t would be dB dt. E's derivative would be e to the b. So we got e to the b times dB dt. Surface area is changing by 10 squared. And watch how like this will help us. If you use units, like how's the base area changing? It should be in squared feet per second. We got e to the b. We got dB dt. The base area is squared feet. If I take feet squared per second and divide it by feet squared, I should get squared feet per second. Why don't I get that? Honestly don't know like what's going on with the units here. uh this like I bet you e to the power gives you the feet. This is actually in feet squared per second. Oh, I don't know, honestly. I have no idea. Whatever. It would be it feels like it needs to be in feet squared per second, but whatever. Not that important. Sometimes helpful, sometimes not. Okay. To a very simple, like real world situation, we have a sphere being blown up. So the sphere is constantly changing. The radius is not always 5 feet. We're asking how fast is the radius of the balloon changing at the moment when r is 5. This is at a moment in time. Think about we're blowing up a spherical balloon. It's always changing. We're going to hit our stopwatch right when the radius is 5 feet, and we're saying how quickly is the volume expanding at that moment. Sorry, how quickly is the radius expanding at that moment? We are given cubic feet per second. That is a dV dt. We have a formula for the volume of a sphere. We'll need to figure out the change formula for the volume of a sphere. This is a really good one that kind of shows relationships and shows how these change equations work. We got this 4/3 pi, which is just a constant. We have r cubed, which is 3r squared times dr dt. Now, if you go ahead and simplify the 3 and the 4/3, probably would help you out a little bit to give you 4 pi r squared. Now, what's interesting is that this is the formula for the surface area of a sphere, 4 pi r squared. So if you know the surface area, how much area is around the sphere, and you know how much the radius is changing, you're actually going to be able to figure out how quickly the volume's changing just by like area times how much this units are changing radius. Think about that if it makes sense. Have a picture of a sphere in your head, like expanding. If you know the area around it and how quickly it's expanding, you'll know how quickly the volume's changing. But not important if you just can do it. Divide by 4 pi and 25. A lot of you like to simplify these numbers, but watch how like I'm not going to simplify until the end if you even need to. This is honestly left for free response. This is totally acceptable. Maybe for multiple choice, you will want to simplify this. Some things you could do is like divide the top and bottom by 2. Divide the top and bottom by 5. And you get 1/10 pi, which is honestly like if you just did 10/100 pi, you would have gotten that. Okay, now we have our volume equation. And we have our surface area equation. Asking how quickly the surface area is changing at the same moment when r is 5 and dv dt is 10. Well, we have our volume change formula, which is related to our surface area. Now we need a surface area change formula, which is going to be interesting we got 8 pi r times dr dt. I brought the 2 down, took the derivative of r squared, 2r dr dt. So the circumference of a circle is 2 pi r. I wonder if we're getting like some sort of spherical equation. Can't explain the 8 pi r, to be honest. Okay, regardless, let's just get into it. What happened? Like, if we were to do this question from scratch, we would have had to find dr dt because I'm trying to find how the surface area is changing. I have r, but I don't know what dr dt is. We're going to have to take this dr dt from the previous question that we found and plug it in here. However, let's pretend that we are doing this just for the first time. We would have to do the work to find dr dt, and then we would have to substitute that into the other equation. This is something that you'll have to get comfortable with substituting. Substitution is important. Pi's cancel. 5 over 10 becomes 1 over 2. 8 divided by 2 is 4. So this would be 4 squared units, squared centimeters per whatever. All right, here is an example of the same thing where we have to kind of start from scratch, use one equation, simplify, solve, and then use it in the other. How fast is the volume of a sphere growing when the radius of the sphere is 2 feet and the surface area of a sphere is growing by 20 square feet? So if you just start with the volume of a sphere formula, which is up above, you realize you need to know how quickly the radius is changing. You are not told how quickly the radius is changing. You're told everything else, but we're going to have to find how quickly the radius is changing. How are we going to find that? Using this information and using our surface area formula, which is 4 pi r squared. Boom. So I have the change formula for the surface area. I have dSA dt is 20. I have r is 2. I want to find dr dt so that I can substitute it in there. So this is an example of maybe we can just keep this like that and then simplify off of that. Turn this into a 10. Turn this into 5 over 4 pi. Substitute that in there. Of course, if you didn't do that, it's fine. It's just like a different strategy of simplifying fractions, which is necessary for free response, for multiple choice, but not necessary for free response. Free response, guys, leave your things unsimplified, and if it's correct, it's correct. Make sure you know that pi is in the denominator. Pi is in the bottom. If you want to multiply everything straight across, you got 4 times pi times 4 times 5 over 4 times pi. These 4s and pi's go away, and you get an answer of 20. Many ways to get that answer of 20. Just so happens the volume is growing at the same rate as the surface area. because the radius is this certain size, not always gonna be like that. How quickly is the sphere's volume changing? When its radius is 3. Circular cross section through the sphere's center is increasing at 4 centimeters per second. I probably should have given you that the area of a circular cross section is the same as the area of a circle, which is pi r squared. I probably should have given you, like, guys, you probably need to use the area of a circle is pi r squared, because the change in the area is 4 of that circular cross section. But you're not using the surface area, you're using a circular cross section, pi r squared. So again, we're using the volume of a sphere. Just one just shows up that's common. R is 3. What is dr dt? We're going to have to find it using the change in a circle's area. That's pi times 2r dr dt. We realize dA dt is 4, r is 3. Two over 3 pi. $24. Well, so relationship of two different formula that are simultaneously occurring in one situation. We got a square. Area of square is increasing by 2 squared feet per second. How fast are the side lengths changing when the length is 4? Well, a equals s squared. Pop a derivative. dA dt equals 2s times ds dt. dA dt is 2. S is 4. ds dt is 1/4. Circles. That's circle. Circle. A circle is growing at some point. The area of the circle is growing at twice the rate of circumference. What is the radius length at that point? It's like a great question, because it's like, what the heck? You're not giving me any information at all, but I'm going to show you the information that you're given. There's a lot of different ways that students get this right, and it shows me their intuitive mathematical thinking. So this is a question where I would just we do in class. And when we do in class, I'm just like, I want you to see if you could figure this out. And if you really understand what's going on, or if you can just kind of set something up, do this algebraically. What I like to do is say the area of the rate of change of the area of the circle is equivalent to twice the rate that the circumference is changing. And have this as something that I can use and substitute in. Some people can just kind of intuitively figure out, okay, this is twice that of this, so I can just double this, and it's great. That is very mathematical, and hold on to that. But if you have no idea what to do, you can just set this up and then substitute. For example, what do I substitute? Maybe substitute this in. Maybe divide by 2, and now we have something where dc dt is equivalent to a version of dr dt. Maybe I substitute that in. Some of you would be able to get this answer intuitively. Now you'll see that the dr dt's cancel, the pi's cancel, and you just get that r is 2. It's pretty cool how that happens. It's not always going to be the same rate. Sometimes it's like reciprocal rates. But it's an interesting one. Now we go to the next one / segue into next class. Next class is a lot of triangles and then understanding what happens when things are constant. Here's what I'm talking about. We got a cylindrical tank. This is like the worst tank I've ever drawn in my life. And I've drawn some pretty bad tanks. Sure, I'll use that. And we got this volume formula, which is pi r squared h. Now, the radius is 2 feet. There's water in this tank, and we're going to examine like the water in the tank. And we're losing water at a rate of 4 cubic feet per second. So we get that dv dt is -4. We're asked to find how the height is changing. That's dh dt. I just got a raindrop. Just breaking barriers here with these videos. So how fast is the height of the water changing as this tank loses water through some sort of leak? Well, when we take the derivative, the first thing that students are going to mess up on is realizing that we have a product, which means we need to use the product rule. You can leave the pi out or bake it into the r squared. You get pi times 2r dr dt h plus the derivative of h, which is dh dt, times pi r squared. And we got what we got. Now, here's the problem. What the heck is dr dt? What the heck is h? You're not giving me enough information. Yes, I am. Yes, I am. Why? Think about the water in this tank. Yes, it's got a radius and it's got a height. Well, as the water starts to drip out, what is changing? Just the height. What's not changing? The radius. The radius of the water is always 2. This is different from our spheres. This is different from our circles, where everything has to change. With certain situations, you're not going to have 2 things changing at once. It's literally raining on me now. This is great. It's great. Let's finish strong. I'm like, the guy who sings Purple Rain at the Super Bowl. Oh my gosh, why can't I think of his name? Who's the guy who sings Purple Rain? No, I gotta get this. Prince. Jeez, I'm just trying to think of like 2 names. It's Prince. Prince. I'm like Prince. I'm like Prince with this video right here. Just like finishing it off in the rain. Make it rain harder to make this video more dramatic. The radius is not changing. The radius is fixed. The radius is constant. dr dt is 0 because the radius is not changing. I don't need h. This whole thing is 0. Now, you also could actually change your original equation from the volume of a cylinder equation to the volume of my water in this tank will always be this. And you could have actually plugged in 4 into, 2 into R squared early on. I actually don't want you to do that because I feel like it's become less of a thing that is done on the AP Calculus exam. Rather, a thing that is more done is using the product rule and finding drdt and dHdt if things are changing. So that's negative 1 over pi. That was your 5.3 homework. I'll see you next class for your quiz. Peace.